Hey everybody, welcome right back to another round of engineering, and let's get moving. So today's topic is the topic of superposition. And I don't mean the superposition like forces or momentum. We're talking circuit superposition. And so what this is the analysis of a circuit according to the individual sources. So let's go ahead and draw out a circuit. Say maybe you have a current supply running through a resistor, which is connected to another potential supply. And notice I'm doing all of these independent supplies here. Let's put another resistor in. Let's put another resistor in. And we'll put one more in for good measure. And why not? We'll put in another current supply. There we go. Something like this. I'm just making something up. Now, what the superposition allows us to do is to consider the contribution of one independent supply while ignoring the contributions of the others. So you could imagine, okay, this circuit with only the current supply that I've indicated, and you go through and you do your analysis. Then you say, okay, I've done it for that one. Now I will work on the contributions of the potential supply, and you'll go ahead and analyze those. Finally, the last current supply, you'll analyze the circuit according to that. And if you want the full operation, if you will, of the entire circuit, you can then take those three individual pieces that you've done and superimpose them. That's what I mean by superposition in the sense of the electronics class. Now, you're probably already thinking it. Yes, this isn't necessarily the most effective method if you want the complete function of the entire circuit, right? Here, for the example that I've given you, actually, you have to solve this circuit 3 times because there's 3 independent sources. So from that standpoint, it's not particularly effective. However, sometimes you'll have questions where you want to know the contribution of a individual source to the overall function of the circuit. And then the principle of superposition will help you out immensely. So there's, again, it depends on the situation. It's going to depend on what question you're trying to answer as to the utility of this method. That being said, we still need to know how to do this method. So how do we go about applying this method of superposition? Well, number one, we identify our independent sources. That is the first thing that we need to do. This principle of superposition only applies for the independent sources. Dependent sources, the diamonds, we have to leave those in the circuit. And the next thing that we need to do is choose one source and deactivate others. And this is probably the most important point of the entire process. What does it mean to deactivate a source? Well, if we have a potential supply, the way to deactivate a potential supply is to make sure that there is not a drop in potential across the branch where the supply is found. Well, how do we do that conceptually? We replace the potential supply with an equipotential. In other words, rather than having a potential supply in a branch, you replace it with an equipotential, a perfect wire. So to deactivate potential supply, just put an equipotential in, a wire. For a current supply, again, we're trying to remove the influence of that current supply altogether. In other words, we don't want any current flowing through that branch. That's how we deactivate it. We remove its influence on the circuit. And so any current supply, you turn into a break. In other words, a path through which no current is available to flow. And hopefully that makes some hopefully that appeals to the intuition. To deactivate a potential supply, we put in an equipotential. To deactivate a current supply, we put in a break. Then solve. Solve circuit. Right. So you solve it for the one source that you've chosen to keep active. And then, of course, the problem here, number 4, rinse, wash, and repeat. In other words, you have to do this not for this single source, but if you want to do it for the entire circuit response, you have to do it for every single source in your circuit. So for this circuit that I've just drawn for illustrative purposes, how many times are you actually going to have to solve this circuit? 3. If you want to know the entire response for the circuit, you're going to have to solve 3 smaller cases, right? One with the leftmost current supply, one with the potential, and one with the rightmost current supply. In fact, take a minute, pause the video, and go ahead, draw out what does the circuit look like when I'm applying, or when I choose the leftmost current supply. Yeah, hopefully you got it. Well, if I keep my leftmost current supply active, well, then I've got that resistor. I need to deactivate my potential supply. So I'm just putting a wire in at that point. And then I have this resistor. I have the second resistor. And you notice that third resistor, I have a break, right? To remove that current supply, the rightmost current supply, that's a break in the line. And so no current's going to flow in that one. So I can get rid of that piece altogether. And so there's the first circuit I have to analyze with the leftmost source active. Go ahead. How about if I choose the potential source? You got it? Yeah, that one looks weird, right? Because now this left and rightmost current supply is deactivated. And so we have simply something like this. And in fact, I'm not quite sure what this circuit does. Right? There's no completed, I guess there's a completed path here, but there's no completed path for the entire circuit. So it might even be that this potential supply doesn't do anything. But the rightmost one, okay, the rightmost one, we've got a break. And so what we have for the rightmost one is just our current supply and our 2 resistors, like this. And if we want the full response of the circuit, we have to take these three responses and add the final answers together. Now, you say, how do I analyze these circuits? By whatever means you find the most convenient. So once you break it into a single source circuit for each of these three cases, then you're free to choose node voltage, mesh current, KVL, KCL, by combining resistors or just straight out Ohm's law. Okay, so you're more than welcome to choose whatever method you want at that point. So let's go ahead and do our example problem with our favorite circuit here. So I've gone ahead and drawn the circuit, and we already know from past lectures the current running through each of the individual resistors. So let's go ahead and apply this principle of superposition to find the current through each of the resistors. Well, first off, we see that we have two independent sources, this one being 5 volts. And so what we're going to do is we are going to model this circuit as two individual circuits with single sources. So we have to solve those two equations. Go ahead, take a minute, solve the circuit. Okay, I'll go for this rightmost circuit first. And the thing I notice is that I've got my 3 ohm resistor is parallel to the 8 ohm resistor. Okay. So yeah, why don't we just do combining resistances? So this would be something like 1/3 plus 1/8 to the -1. So what does this give us? This gives us 8/24 plus 3/24, all inverted. So something like 24/11 ohms. So now I've got something, the total resistance, Req, of that circuit. The 24/11 ohms refers to the two parallel branches, and that itself is in series with the 1 ohm branch. So I can add in series, so I get something that says 35/11 omega is the overall resistance. Well, now I can apply Ohm's law. And I'll put EQ here. I've got the potential 10. So I can find the current coming from that 10 volt source. I get a current of, well, 10 divided by 35/11. So we get that compound fraction going. And so I've got something like 110 divided by 35. But it's divisible by 5. So what is this? This is 22. 22 divided by 7. There we go. Amps. So that's coming from the 10 volt supply. Then what we have to do is then go back and figure out how much goes through the 3 ohm branch, how much goes through the 8 ohm branch. This is a current divider at this point, right? Now, if you don't remember, we could go ahead and apply Ohm's law and that kind of thing. I'll go ahead and skip to the final answer here. The current through the 3 ohm branch, I always think of it as the path of least resistance. Okay. So the current through the 3 ohm branch is going to be something like 8 divided by 11. You notice, where did I get the 8 from? Yeah, it's that bottom resistor, and 11 is the summation of the two resistors. Okay. So 8/11 times the original current. So I'll put times 22 over 7. That is how much will go through the 3 ohm branch. Okay. Similarly, for the 8 ohm branch, okay, 3 over 11. So you can kind of get a sense of the path of least resistance. As one branch becomes less and less resistive, more current will flow through the other branch, right? Or that branch, I should say. So as the 3 ohm branch, if I were able to crank down the resistance there, you can see that less and less current would go through the 8 ohm resistor. There we go. So we get rid of those. And this is, again, 22 over 7. That's to make sure that they divide current and maintain that charge conservation that we saw. And so at the end of the day, we get something like 16 over 7 and 6 over 7 amps. But wait, we're not done. Because unfortunately, we've only done this first circuit. Right? We've only done that first piece. We still need to do the second piece, the second circuit here. So that's why I say sometimes this doesn't yield any time advantages, but the upshot is I can say the 10-volt supply provides this amount of current to each of the components. Go ahead, take a shot at the second one. You got it? Well, we probably can hack out everything we need right here. We notice that instead of the 8 and the 3 ohm resistor being in parallel, it's the 8 and the 1 ohm resistor. So we have the 1 ohm resistor parallel to the 8 ohm resistor. And so the equivalence resistance of that combination, 1 over 1 plus 1 over 8 to the negative 1. And so you're going to get something like, well, 8 over 8. Excuse me, I was 8 over 8. So we get 9 over 8. So we get 8 over 9 ohms. Well, if it's 8 over 9 ohms for the parallel branches, that means the overall resistance, the total resistance, we have that 3 ohm resistor in there. So we need another 27/9 added to this. So we get 35 over 9. Right, 27 plus 8. There we go. Well, if it's 38 over 9, that means that the current provided by the 5-volt source, so this was the 10-volt source, the current provided by the 5-volt source is 5 divided by 35/9, or if you prefer, 9/7 of an amp. And then we have our current division. The current flowing through the 1 ohm resistor due to this 5-volt supply will be, well, let's see, 1 plus 8 is 9, and I'll put 8 here. And then we have our total current, 9/7, and so we find that 8/7 of an amp due to the 5-volt supply, and I8, the current running through resistor 8, will be 1/9 of 9/7, which will of course give us 1/7 of an amp. Boom. Cool, we're done. Of course, while I say we're done, the last thing that we need to do is we need to add everything in order to get an idea about the overall current, right? We've now analyzed the individual circuits. Now we have to put it all back together. And the piece that we have to be careful of here is keeping in mind which direction the currents are flowing. Okay. So for the 10-volt supply, 22/7, and let me do this in a different color here. Let's do it in green. For the 10-volt supply, when we were doing the 10-volt stuff, this 22/7 of an amp is running, I'll do this one in green, is running this way. In fact, I guess it would probably be better if I did it on this figure, right? The 22/7 of an amp are running this way. For the 5-volt one, you know, it's almost like a fountain, right? They're going that way. So you have to pay attention when we're doing the superposition. If they're in the same direction, they need to be added together. If they're in opposite directions, they need to be subtracted. We have to take the difference. Okay. So, well, for the 1 ohm resistor, let's go ahead and take a 1 ohm resistor. We have 22/7 of an amp running from right to left due to the 10-volt potential. We have 8/7 of an amp running from left to right due to the 5-volt potential. And so overall, we're going to have to take the difference of those two. Okay. Well, the difference of those two is 22 minus 8, 14. And 14 divided by 7 is 2. So at the end of the day, we get 2 amps here. I've written this in the upper hand corner. I guess the other way you do it is I could always write out the values. There's a 22/7 of an amp there. There's an 8/7 of an amp here. Well, how about the 3-volt or the 3 ohm? Well, the 3 ohm had 16/7 of an amp from the first situation. And from the second situation, it had 9/7. Like I said, I'm just doing that in green. And notice again, they're running in opposite directions, which means I need to subtract the two. So 16 minus 9, 7. 7 divided by 7 is 1. And so we get that there must be 1 amp of current flowing from left to right in the 3 ohm resistor. Last one, of course you see it, the 1/7 and the 6/7 flowing through resistor 8 are in the same direction, and so we get 1 amp again. And we're done. Cool, huh? Shall we take another crack at it? Okay. Let's do this one. Let us go ahead and find the value of I naught using superposition. Sweet. Okay. Excuse me. Let's go at it. And again, I tend to just draw out my figures. Sometimes after a while, when you get really good at it, you can start maybe using the one figure and then writing down all of your stuff and then just doing it. I would encourage you, as you're learning it and building familiarity, I would encourage you to just quickly draw out the figure several times just to help with the visualization aspects. So, well, what do we have here? We have, I'll go ahead and do the 6 amp source first. So we have the 6 amp source, and I'll drop the labels for sake of speed, but also in the sense of I'm just redrawing, so I have the numbers on the regular figure. Now, this 10 amp source is deactivated, so I don't have to actually put anything there. I'm going to skip that. I'll just note that there used to be a node there. Okay? And I'll keep going. So now I've got my 60. Okay. I've got my 5, and I'm deactivating my potential supply. So I just connect the 5 to a wire. And then I've got that 30 right there. Okay. Well, how do we want to go at this? Let's go ahead and do node voltage. Sure, let's do node voltage. Okay. So I'm going to choose my 3 nodes. We've got node A up here. Call that one A. Call this one B. And then we'll have C down here. And now we just go at it like a bale of turtles. If I'm looking at node A, I've got something like -6 coming in. Oh, and I'll ground node C, excuse me. Tend to ground the one on the bottom anyway. Okay, yes, I've got -6 coming in, and then I've got the potential of A divided by 20. And then I've got the potential of A minus the potential of B over 1 equals 0. For B, I have negative VB, minus VA over 1. Okay. And then I've got a bunch of rigmarole, right? I've got plus VB divided by 60 plus VB divided by 5 plus VB divided by 30 equals 0. So now I can sub and solve. Okay. And so what I have at the end of the day is VA VB is equal to 24 and 19.2 volts. Now, if we're just concerned with I naught, that means, right here, we're just concerned with I naught, so I can find the contribution now. Right, the contribution to I naught from the 6 amp source is equal to the difference of those two, VA minus VB divided by 1. And so I get something like 4.8. All right, 4.8 amps goes through I1, and the rest gets siphoned through that 20 ohm resistor. So there we go. We've got the first one. So let's go ahead and work on that second circuit. Now I've got a break for the 6 amp supply, so I don't need to worry about that. I've got this 20 ohm resistor and this 1 ohm resistor. We've got this 10 amp supply going downwards now. Okay. We've got our 60 volts, or excuse me, 60 ohms. We've got our 5 ohm resistor, and we've got our 30 ohm resistor. And that's it. So let's go ahead. I'll do node voltage again. And now we notice that because that 6 amp source is deactivated, we do not have that node right here at the corner again. That was node A in the previous analysis. That is no longer an essential node. So all we have are 2 essential nodes, say node B and node C. I'll go ahead and ground. There we go. So this one might even be faster. We don't have to sub and solve even. We'll just write down our equation and we'll have our answer. So let's go at it. We have VB over 21. That's that left route. And then here we have that 10 amps leaving the node. And added to that, we have VB over 60 plus VB over 5 plus VB over 30 equals 0. Well, spiffy. Move the 10 to the other side, so we get that negative 10 here. And I don't know, I'm sure we could come up with it, but let's go ahead and just check it real fast. There we go. I get something like VB times 25 over 84 equals negative 10. Okay. And so we have VB is equal to negative 840 over 25, which I'm sure can be simplified. Well, yeah, of course it can. Excuse me. Should just simplify it while we're going at it. This 10 turns into a 2. This 25 is a 5. And so we get 2 times 84. So that's 168 divided by 5. There we go. Which means, let's go ahead and find it, the contribution to I naught from the 10 amp supply is VB, don't forget the negative sign, VB divided by 21. That 21 is the branch that contains the 1 ohm resistor and the 20 ohm resistor, since there's no junction right now. And so what do we get here? Negative 168 divided by 21 times 5. Yeah, I'm not seeing it. Might be a common 7 in there somewhere. Yep. Must be a common 7 and a common 7 and a common 3. This ends up being 8/5. So 1.6 amps. Notice the negative sign, which I've tried to drop twice. And the fact that we have a negative sign means it's going into node B, not away. And so this current is going from left to right, as was this current, left to right. Well, let's go ahead and jump to a new page and get the third answer. There we go. And so we have, again, a deactivated 10 volt or 10 amp supply. We have a deactivated 6 amp supply. And so we have this circuit awaiting for us. And again, we could probably do, I personally like node voltage. That tends to be the one that I use the most often. And yeah, if we ground this side, we see that this side has to be at 75 minus that 5 volt, that 5 ohm thing. Okay, well, let's go at it. Again, we only have one node, and so we'll go ahead and write down our equation. I'll call it VA here. So we have VA divided by 21 plus VA divided by 60 plus VA minus 75 over 5 plus VA over 30 equals 0. And we're good to go. So you get what? VA, it's 1 over 21. So again, we get VA times 25 over 84 is equal to, Well, this 75 over 5, that's 15. So we get 15 here. It's 5, this is a 3. And so we finally get that the potential at A, okay, I got 50.4. There we go. So again, if we want the current I naught due to the 75 volt supply, we should take VA and divide by the path, which was 21 ohms. So let's go ahead and do that. Divided by 21. And I get something that says 2.4 amps. And again, this one, if we look at the figure again, this is from left to right. Well, so what do we have? At the end of the day, so because we have a positive value, we've noticed the current direction of the currents. So I naught, the total, would be 4.8. That's from the 6 amp source, plus the 1.6, that's from the 10 amp source, minus 2.4. And that's coming from the 75 volt supply. So what do we have at the end of the day? Well, let's see, 2.4 plus 1.6. So I get something like 4 amps as our total for I naught. Cool. Okay. Well, I think that that's probably a convenient place to leave you for right now. I'll get another video posted here after I get this one edited and cleaned up. And yeah, we'll keep moving forward. Thanks for your attention. I'll see you next time.